Look out of an aeroplane window on your next flight. It has rounded corners. Every window on every airliner in the world has rounded corners. It is one of those design details that is so consistent and so quiet that you have probably never once wondered why. The answer is that in 1954, aircraft had square windows, and two of them came apart in mid-air. And the people who worked out why did something that has almost no equal in engineering history. And the most repeated version of this story, the one you may already know, is wrong in a specific and interesting way. Start with what the comet was. The de Havilland Comet was the first jet airliner in the world, not the first fast plane, the first passenger jet. It entered service in 1952, and Britain had built it, and for 2 years it was genuinely years ahead of anything the Americans had. It flew higher than propeller aircraft, which meant above the weather. It flew faster. It was smooth and quiet in a way passengers had never experienced. To fly that high, the cabin had to be pressurized much harder than anything before it. Every flight, the fuselage inflated slightly like a balloon, and on landing it deflated again. Nobody at the time fully understood what doing that thousands of times would do to aluminium. On the 10th of January 1954, a comet registered GA Lip left Rome for London. It was climbing out over the Mediterranean when it broke apart in the air. It fell into the sea near the island of Elba. All 35 people on board were killed, 29 passengers and 6 crew. The fleet was grounded. Modifications were made. Nobody knew the real cause yet, so the changes were educated guesses. 10 weeks later, the comets were flying again. And on the 8th of April, another comet, flying for South African Airways from Rome to Cairo, broke apart in the air and fell into the sea. 21 people this time, 14 passengers and 7 crew. 2 aircraft, same type, same route, out of the same airport, both coming apart at altitude within 3 months. Here is where the story becomes something else. The obvious problem is that the evidence is at the bottom of the Mediterranean. You cannot investigate what you cannot hold. So the Royal Aircraft Establishment at Farnborough did 2 things at once. The first was to recover the wreckage, not some of it. The Royal Navy salvaged pieces of the first aircraft off the sea floor, and the team laid what they found out on a wooden frame shaped like the aeroplane, reassembling the fuselage from fragments. The second thing they did is the part worth remembering. They took a whole other comet, a working one, registration GALYU, and they built an enormous water tank around it. Then they filled the tank and pumped water into the aircraft and let it out again. Over and over. Each cycle stood in for one flight's pressurization. Water, not air, because air at that pressure holds enormous energy, and a failure would have destroyed the evidence in the explosion. Water is nearly incompressible. When it fails, it simply stops. They ran it 24 hours a day, 7 days a week, and after the equivalent of around 3,000 flights, the fuselage failed in the tank, in a laboratory, where they could watch it happen and photograph exactly where it started. That is the whole investigation in one sentence. They could not read the accident, so they built a machine to repeat it until it happened in front of them. Now the part that most tellings get wrong. The version everybody repeats is, the windows were square, the corners concentrated stress, the corners cracked, the aeroplane came apart, and that is why windows are round now. The conclusion is right, the specific detail is not. On GALYP, the aircraft that broke up near Elba, the failure of the pressure cabin started at the forward automatic direction finder window in the roof. That is an antenna aperture covered by a fiberglass panel, not a passenger window at all. And the Court of Inquiry, reporting in February 1955, found something else that mattered as much as the shape. The panels around those openings had been attached with punch rivets rather than being glued, and that method left tiny cracks in the metal around the holes before the aircraft had flown a single mile. So the honest version is, it was not simply that the windows were square. It was that any sharp-cornered opening in a pressure vessel concentrates stress, and this aircraft had several, and the way they had been fastened had already started the cracks for you, which is why the fix generalized. Round the corners of every aperture, everywhere, not just the ones passengers look through. A curve has no single point for stress to pile up on. It spreads the load along the arc, instead of driving it into a corner. That is why your window is a rounded rectangle, and it is why the emergency exits, the cargo doors, and the access panels are too. Look next time. Nothing on a modern fuselage has a sharp corner. The Comet 1 never carried passengers again. De Havilland lost its lead, and Boeing took the jet airliner market with the 707 and never gave it back. 3 fatal Comet crashes killed 99 people in total. But the industry got something from those investigations that it still uses every day. Before the Comet, full-scale fatigue testing of a pressurized airframe was not standard practice. After it, it was. Every airliner you have ever flown on has a sibling that was cycled to destruction in a rig on the ground, so that the one carrying you would not be the one to find the limit. That is the actual legacy, not the round corners. The round corners are just the part you can see. The industry learned to break things on purpose, carefully, in a tank, so that they would not break by accident at 30,000 feet with people inside. Next time you sit down and look out at the wing, run your finger around the edge of the window. Somebody worked that curve out the hard way, and everyone who has flown since has been riding on the.
In 1992, a vacuum cleaner company in Britain made an offer. Spend £100 on Hoover products and they would give you 2 free plane tickets. Not a discount, not a raffle, 2 return flights, and you could pick America. Those tickets were worth about £600. The vacuum cost you $100. So the free gift was worth 6 times the thing you had to buy to get it. Somebody at Hoover signed off on that. And within a year, it took down a company so famous that British people still use its name as a verb. Start with why anyone thought this was a good idea. Hoover was not a small brand. In Britain, it owned about half the vacuum market. People didn't say they were vacuuming the carpet, they said they were hoovering it. That is the level of household name we're talking about. But by 1992, the warehouses were full. Hoover had far too much stock and a recession outside the door, and somebody needed a plan to move it. The logic went like this. Free flights sound enormous, so people will come in. Most of them will never actually claim. That's how promotions work. You dangle something huge, and the paperwork quietly eats most of it. They budgeted for around 50,000 people to follow through. There's a word for the assumption underneath that number. They assumed people were lazy. In November, they made it worse. The original offer was flights inside Europe. In November 1992, they added American destinations. Now the prize wasn't a weekend in Paris, it was New York. And this is the moment the thing turned. Because the moment American flights were on the table, people did the arithmetic. 2 tickets to the United States for £100 of vacuum cleaner. You didn't need to want a vacuum cleaner, you just needed to want to go to America. So people stopped buying vacuums as vacuums. They started buying the cheapest £100 of Hoover product that qualified, purely as a ticket. Some bought machines they never took out of the box. Newspapers ran stories about people trying to sell brand new Hoovers for £40 because they had already got what they actually came for. Hoover had planned for 50,000 applications. They got around 300,000. 300,000 people, 2 tickets each, 600,000 flights. The promotion had generated about £30 million in sales. The flights they now owed were worth well over $100 million. They had sold £30 million of vacuum cleaners in exchange for a debt 3 times larger. Here is where most versions of this story stop. A company made a maths error, lost a lot of money. Embarrassing. The end. That is not the interesting part. The interesting part is what Hoover did next. They could not afford the flights. And rather than say that, they started trying to make their own customers give up. They began telling people the forms had been filled in wrong, thousands of them. Small errors, technicalities, buried conditions. They offered flights leaving from airports hundreds of miles from where customers actually lived. Technically an offer, practically impossible. And they posted request forms so they landed on Christmas Eve, when the post offices were closing against deadlines the customer could no longer meet. That one wasn't carelessness. You have to choose that date. One executive said it out loud, and it was reported. The whole idea was to put people off going because every single customer who actually flew cost Hoover money. That's the sentence that turns this from a business mistake into something else. The company was no longer trying to serve the customer or even to save money quietly. It was actively working against the people who had bought its products. British people are patient, and then they are not. A man named Harry Sitchie started a group for people who'd been promised flights and got nothing, the Hoover Holiday Pressure Group. It ended up with more than 4,000 members. Ordinary people, comparing letters, realizing they were all getting the same excuses. And in June 1993, a customer called Dave Dixon did something simpler. He found a Hoover delivery van and he stopped it from leaving. For 13 days. Not a lawsuit, not a letter to the paper, one man and a van for nearly 2 weeks in front of cameras. The bill came in pieces. 3 senior executives lost their jobs: the managing director, the vice president of marketing, and the director of marketing services, fired over a sales promotion. Maytag, the American parent company, eventually paid around $72 million to settle with roughly 220,000 customers. But between 300 and 350,000 people never got what they were promised at all. Hoover's share of the British vacuum market fell from about half to under 10%. Their machines started appearing at the bottom of reliability surveys, and the royal warrant was withdrawn. That's the formal permission to say you supply the royal household, held for decades. Gone. In 1995, Maytag sold Hoover Europe to an Italian competitor called Candy for about $106 million. That sale was booked at a loss of roughly $81 million. The lawsuits ran on until 1998, 6 years after somebody thought free flights would help clear the warehouse. So what actually went wrong here? It wasn't the arithmetic. Anyone can get a number wrong. It was one assumption underneath the arithmetic, that most people would not bother to claim what they had been promised. That assumption is everywhere. It's in the rebate you have to post, the subscription that's 1 click to start and 6 to stop, the refund that requires a phone call at a particular hour. Every one of those is a company quietly betting that you will give up. Usually, it works. It worked for years before Hoover, and it works right now, today. Hoover's mistake was making the prize so enormous that giving up stopped being the easy option. They offered £600 to people who had spent $100. And at that price, people did not get tired. They formed groups, they blocked vans, they stayed angry for 6 years. The company that taught Britain to call vacuuming hoovering was sold off at a loss by the people who had done the maths. And they were only wrong about one thing. They thought nobody would bother.
In August 2026, a team inside Google put up a job application form with an unusual promise on it. It said that if you filled this one out, a real human being would read what you wrote. Which raises the obvious question: what happens to the applications that go through the normal system? The team that posted this is not a random corner of Google. It is the AGI Safety and Alignment team at Google DeepMind. Their job, in the simplest possible terms, is to make sure advanced artificial intelligence behaves. And they had quietly built themselves a way around their own company's artificial intelligence. Bloomberg reported this on the 10th of August, after seeing the internal document. The wording is worth hearing exactly as it was written, because it is not vague and it is not hedged very much. It said, quote, "We have an application system with a non-trivial probability your CV will be screened out incorrectly or take too long to reach us." Non-trivial probability. That is careful, technical language for a real chance this thing throws you away by mistake. And then, quote, "Filling out this form makes sure that a real human on the team will get to see your application." Read those two sentences next to each other. The first says the automated system might lose you. The second offers a door around it. Now, to be fair, and this matters, Google does not accept that reading. A Google DeepMind spokesperson said the company aims to recruit and hire the most qualified talent at Google DeepMind, and denied that its systems filter applicants out incorrectly. Their explanation for the form is simpler than the one everybody jumped to. It is a way for the team to receive CVs directly, not a rescue hatch, just a direct line. That is a real defense, and it is not obviously wrong. Plenty of teams inside big companies keep a side channel for candidates they are actively hunting. But it does sit slightly awkwardly next to the sentence in their own document, which did not say this is a faster route. It said your CV might be screened out incorrectly. Both of those things came from the same company in the same week. You can decide which one you find more convincing. Here is the part that got much less attention, and it is the better story. The same form asked applicants for something else. It asked them to keep their use of AI limited when writing their answers. And it gave a reason. Quote, "These humans get really tired of reading LLM answers because they all sound very samey." Sit with that for a second. This is the Artificial General Intelligence Safety Team at the company that will sell you an AI writing assistant, asking job applicants, "Please write it yourself, because we cannot face reading another one that sounds like all the others." That single sentence describes the entire modern hiring process better than any report has. Because look at what is actually happening on both ends. The applicant opens a language model and asks it to write a cover letter. It produces something competent, polite, structurally perfect, and completely indistinguishable from the 400 other competent, polite, structurally perfect letters that arrive that week. The company, drowning in those, points its own automated system at the pile to sort it. So one machine writes it, another machine reads it, and two humans who might genuinely have wanted to work together never actually make contact. The safety team noticed they were inside that loop and did the only sensible thing. They stepped outside it and asked people to talk to them like people. There is something worth pointing out about who is doing the noticing here. These are not people who dislike this technology. This is their field. They chose it. They spend their working lives on the question of whether these systems can be trusted with things that matter. And when the thing that mattered was their own hiring, the answer they arrived at, in writing, was, "Let's have a human look." That is not hypocrisy. It is calibration. Knowing exactly what a tool is good at is also knowing where it should not be the last word. The people closest to a technology are very often the least romantic about it. The uncomfortable part is what this says about everyone who does not have a side door. The DeepMind team could build one because it is their company. They knew the system, they knew its weak points, and they had the standing to route around it. Almost nobody applying for almost any job has that. You submit into the front of the system and you hear nothing back. And you have no way of knowing whether a person ever saw it or whether you were filtered in the first 4 seconds for a reason nobody will ever tell you. The silence is the same either way. That is what makes it corrosive. Not being rejected, not knowing whether you were ever read. So, what do you actually do with this? The practical lesson is not clever. It is the oldest advice in hiring, and it just got confirmed by the people building the machines. Find the human. Every time there is any route to a person who actually does the work, take that route instead of the front door. A short message to someone on the team beats a perfect application into a queue. And when you do get to that person, sound like yourself. Not because authenticity is a virtue, because after 400 flawless machine-written paragraphs, a real sentence from a real person is the only thing left that stands out. The AI safety team wrote that down as a request. It reads better as a warning. They are not worried the machine will be too harsh with you. They are worried it will not notice you at all.
For most of the last century, the search for life in the solar system worked off one idea. Find the zone where a planet is the right distance from the sun for liquid water. Not too hot, not too cold. The habitable zone, the Goldilocks zone. In our solar system, that zone contains Earth and arguably Mars, and that's it. That idea is now largely obsolete, and the thing that broke it is this. The two most promising places we know of are both far outside it. One of them is 5 times further from the sun than Earth. The other is nearly 10 times further, in a place cold enough to freeze nitrogen. Both of them are almost certainly hiding oceans of liquid water right now, under ice, kept warm by something that has nothing to do with sunlight. So I'm gonna go through every place in this solar system where life could plausibly exist today. Not in the past, not in theory, today, and rank them. I'll tell you exactly what's there, what the evidence actually is, what would have to be true, and which ones we are currently flying spacecraft toward. There are more of them than you think, and the top of this list has better odds than most people would guess. First, the ranking method, because otherwise, this is just a list of moons. I'm scoring each place on 3 things. 1, is there liquid water, or a liquid solvent of some kind, right now? Not evidence of ancient water, present tense. 2, is there an energy source? Life needs a chemical gradient to eat, something out of equilibrium that it can push toward equilibrium and harvest the difference. On Earth's surface, that's sunlight. In the deep ocean, it's chemistry at hydrothermal vents. And that's the model that matters here because sunlight is useless under 15 kilometers of ice. 3 are the raw ingredients there. Carbon, nitrogen, phosphorus, sulfur. The boring stuff. A place that scores on all 3 isn't proof of life. It's a place where we can't rule it out, which in this field is a much bigger deal than it sounds. Because for most of the solar system, we can rule it out immediately. And I want to be honest about the standard here up front. We have exactly 1 example of life in the entire universe. Every rule we have about what life needs is derived from a sample size of 1. That's a genuinely weak basis for confident predictions, and it cuts both ways. We might be too strict, or we might be missing possibilities we can't imagine. Let's start with the ones that fail, because knowing why they failed tells you what actually matters. Mercury fails on everything. No atmosphere to speak of, surface swinging from 430 degrees Celsius in daylight to minus 180 at night. There is water ice in permanently shadowed craters at the poles, genuinely confirmed, but it's frozen solid with no energy source and no liquid phase. Dead. Our own moon? Same story. Confirmed water ice at the poles, extremely valuable for future missions, useless for life. Io, the innermost large moon of Jupiter, is the interesting failure. It is the most volcanically active body in the solar system. Hundreds of active volcanoes, lava lakes, plumes hundreds of kilometers high. It has energy in absurd abundance, from tidal heating, which I'll explain properly in a moment. But Io has no water. Jupiter's radiation and the constant volcanism have stripped it. It's a world of molten silicate rock and sulfur compounds. Energy without solvent. And that's the useful lesson. Energy alone isn't enough, and water alone isn't enough. Mercury has water without energy. Io has energy without water. Both are dead. The places that matter are the ones that have both. And once you go looking for that combination, you find it in a lot of unexpected places. Which brings us to number 9 on the list, and it's the strangest entry here. Number 9, the clouds of Venus. The surface of Venus is 465 degrees Celsius under 90 times Earth's atmospheric pressure. Nothing survives that. But go up about 50 kilometers and something odd happens. The temperature drops to somewhere between 0 and 50 degrees Celsius, and the pressure is close to Earth's at sea level. There's a band in the Venusian atmosphere that is, in terms of temperature and pressure, the most Earth-like environment in the solar system outside Earth. The catch is enormous. Those clouds are concentrated sulfuric acid, not diluted, concentrated, and there is essentially no liquid water. Any organism there would have to survive an acidity many orders of magnitude beyond anything on Earth and float permanently, because falling means being cooked. In 2020, a team reported detecting phosphine in the Venusian atmosphere, a gas that on Earth is associated with biological processes and that shouldn't survive long in that environment. It caused a genuine sensation. And then it got messy. Reanalyses of the same data found the signal much weaker or absent. Other groups disputed the statistical treatment. Later observations have gone both ways, and there are now proposed non-biological explanations involving volcanic chemistry. Where it honestly stands? Unresolved and contested, leaning skeptical. I'm including Venus because the temperature band is real and the question is legitimately open, not because I think there's anything alive there. Private missions are being planned to fly through those clouds and sample them directly, which is the only way this gets settled. Ranked 9th because the acid problem is brutal. Number 8, Ceres, the largest object in the asteroid belt, and a place almost nobody thinks about. Ceres is a dwarf planet about 940 kilometers across. When NASA's Dawn spacecraft arrived, it photographed bright spots inside Oakator crater that turned out to be salt deposits, sodium carbonate, left behind by briny liquid that reached the surface and evaporated. That implies a subsurface reservoir of salty liquid water, and the evidence suggests some of it may still be liquid today, kept from freezing by dissolved salts rather than by heat. Dawn also detected organic compounds near Ernetet crater. So, possible present-day brine, organics confirmed, and a body small enough that we could realistically land and drill. Why only 8th? Energy. Ceres has no large planet nearby to squeeze it, and it's too small to have retained much internal heat. Without a strong energy gradient, you have a cold, salty puddle with interesting chemistry and nothing to power a metabolism. Still, it's the closest object on this entire list, and that matters more than it sounds. Access is a real variable. Number 7 and 6, Callisto and Ganymede, 2 of Jupiter's other large moons. Ganymede is the largest moon in the solar system, bigger than Mercury. It's also the only moon known to generate its own magnetic field, and that turned out to be the clue. Hubble observations of the aurorae at Ganymede's poles showed they rock back and forth less than they should if the moon were solid rock and ice. The best explanation is a conducting layer underneath, a salty ocean, buried under something like 150 kilometers of ice, possibly containing more water than all of Earth's surface water combined. Callisto, further out, shows similar magnetic evidence for a subsurface ocean and has the distinction of being the least geologically active large moon around Jupiter. It sits outside the worst of the radiation, which makes it a candidate for a future human outpost. The problem with both is depth and contact. On Ganymede, the ocean may be sandwiched between layers of high-pressure ice that forms under extreme pressure and stays solid even when warm. If the water never touches rock, you lose the mineral chemistry that a deep-sea ecosystem runs on. You'd have a very large, very clean, very isolated body of water with nothing to eat. Europa's ocean, by contrast, is thought to sit directly on rock. That difference is the entire reason Europa ranks where it does, and Ganymede doesn't. The European Space Agency's JUICE mission launched in 2023 and will enter orbit around Ganymede in the 2030s, the first spacecraft ever to orbit a moon other than our own. Number 5, Triton, Neptune's largest moon and the one nobody has been back to. Voyager 2 flew past Triton in 1989 and returned images that made no sense for an object that far out. The surface was young, very few impact craters, meaning it's being resurfaced. And there were dark streaks across the southern polar cap, apparently from geysers erupting nitrogen gas and dust several kilometers up. Triton is minus 235 degrees Celsius. It is one of the coldest objects ever measured in the solar system, and it is geologically active. Triton also orbits Neptune backwards, which is the giveaway. It almost certainly formed elsewhere in the Kuiper Belt and was captured. Capture would have caused enormous tidal heating early on, potentially melting the interior completely, and there may still be a subsurface ocean today, possibly kept liquid by ammonia acting as antifreeze. The reason it's fifth and not higher is simply that we know almost nothing. One flyby 37 years ago and no mission since. It's a candidate on the strength of a single afternoon of data. Number 4, Mars. Mars is the one everyone expects at the top, and there's a good reason it isn't. Ancient Mars almost certainly had liquid water on the surface, river valleys, deltas, lake beds, clay minerals that only form in water. Curiosity found organic molecules in mudstone. Perseverance is currently collecting samples in Jezero Crater, an ancient river delta. And in 2024, it found a rock with chemical signatures that a team described as a potential biosignature, with heavy emphasis on potential, and with alternative non-biological explanations still on the table. But that's the past. Today, the Martian surface is a terrible place for life. Average minus 60 degrees Celsius, atmospheric pressure less than 1% of Earth's. So liquid water on the surface boils and freezes almost simultaneously, and no magnetic field or ozone layer, so the surface is sterilized by ultraviolet and cosmic radiation. Present-day Mars is a candidate only underground. There, radiation is blocked, and there may be deep aquifers of salty water. Radar data from the Mars Express orbiter suggested liquid water beneath the south polar cap, though later analyses argued the same signal could come from clays or frozen brines, and that remains disputed. There's also the methane puzzle. Curiosity has repeatedly measured methane in Gale Crater that rises and falls seasonally, while the Trace Gas Orbiter has struggled to detect it from above. Nobody has a settled explanation. It could be geology, it could be something else. Mars is fourth because the present-day habitable zone there is deep, small, and hard to reach. But it's also the one place on this list where we're actively collecting samples for return to Earth. Number 3, Titan. The strangest world in the solar system, and the only entry here where the life wouldn't be water-based. Titan is Saturn's largest moon, bigger than Mercury, and the only moon with a substantial atmosphere. Nitrogen, denser at the surface than Earth's. It's minus 179 degrees Celsius. At that temperature, methane and ethane are liquid. Titan has weather made of them: clouds, rain, rivers that carve channels, and seas. Kraken Mare is larger than any lake on Earth. Cassini's radar mapped coastlines, islands, and estuaries. So Titan has a full liquid cycle, complex organic chemistry falling constantly from the sky as haze, and abundant carbon. What it doesn't have is liquid water at the surface, though it very likely has a water ocean deep underneath, mixed with ammonia, which gives Titan 2 independent shots: a conventional subsurface water ocean, or something genuinely alien in the methane lakes. Life using liquid methane as its solvent instead of water. That's speculative, and the chemistry is hard. Reactions run far slower at that temperature, but it's not ruled out. And Titan is the only place we know where it could even be attempted. NASA's Dragonfly mission is a nuclear-powered rotorcraft that will fly from site to site across Titan's surface, sampling the chemistry directly. It's scheduled to launch in 2028 and arrive in the mid-2030s. Titan is third because the case is genuinely strong, but the biochemistry required is unproven anywhere. Number 2, Enceladus, a moon of Saturn only 500 kilometers across, small enough to fit inside Thailand, and the place where we have already sampled the ocean without landing. In 2005, Cassini spotted plumes erupting from fractures near Enceladus' south pole, jetting water vapor and ice hundreds of kilometers into space. Then Cassini did something remarkable. It flew directly through them, repeatedly, and analyzed the contents. Here's what was in there. Water, obviously. Salts, sodium chloride, meaning the ocean is in contact with rock. Silica nanoparticles, which on Earth form when water above about 90 degrees Celsius interacts with rock. Direct evidence of hydrothermal activity on the seafloor. Molecular hydrogen, which is a usable food source for microbes. Methane, complex organic molecules containing hundreds of atoms. And in 2023, phosphates, phosphorus, the ingredient people had worried might be missing, found at concentrations far higher than in Earth's oceans. Put that together, and Enceladus has every single item on the checklist. Liquid water in contact with rock, a chemical energy gradient from hydrothermal vents, and all the essential elements, including the one we were worried about. We have not detected life there, but we have detected an environment that on Earth would be full of it. It's second only because Europa's ocean is far larger and older, and size and time matter for the odds. Enceladus is arguably the easier target, though. The ocean sprays itself into space, so a future mission can sample it by flying through the plume, with no drilling required.
Number 1. Europa. Europa is Jupiter's fourth largest moon, slightly smaller than our own. Its surface is water ice, and it is the smoothest solid surface in the solar system. Almost no impact craters, which means it's young and constantly renewed. It's covered in a network of long, dark cracks, and in places the ice looks broken into rafts that shifted and refroze exactly like sea ice on Earth. Underneath is an ocean of liquid salt water, somewhere between 60 and 150 kilometers deep. Europa is a quarter of Earth's diameter, but because that ocean covers the entire moon and is so deep, it holds roughly twice as much liquid water as every ocean on Earth combined. Now, how does it stay liquid 5 times further from the sun than we are at minus 160 degrees on the surface? Tidal heating. Europa orbits Jupiter in an ellipse, so the gravitational pull on it varies through each orbit. The moon is stretched and relaxed over and over. That flexing generates friction inside the rock and ice, and friction generates heat. It's the same reason a paperclip gets hot when you bend it back and forth. And critically, this is powered by orbital mechanics, not by the sun. It works just as well in permanent darkness. This is the single idea that broke the habitable zone concept, because it means the amount of sunlight a world receives has nothing to do with whether it can host liquid water. Europa's ocean is believed to sit directly on a rocky seafloor, which means the same water-rock chemistry that powers hydrothermal vent ecosystems on Earth, where entire food webs live on chemical energy with no sunlight at all, and where many researchers think life on Earth began. Europa Clipper launched in October 2024 and arrives in 2030. It won't land. It will make dozens of close flybys, mapping the ice, measuring the ocean's depth and saltiness, and analyzing any plume material it can catch, building the case for whether a lander is worth sending. So here's the whole list, ranked. Europa first, the largest ocean on rock heated by orbital mechanics with a spacecraft already on the way. Enceladus second, every box ticked, and it sprays its ocean into space for free sampling. Titan third, a complete liquid cycle and possibly a second alien biochemistry. Mars fourth, the past looks promising. The present is underground and hard to reach, and it's the only one we're returning samples from. Triton fifth, geologically active at minus 235 degrees, and we visited once. Ganymede and Callisto, 6th and 7th, enormous oceans, probably sealed away from rock. Ceres 8th, brine and organics, no energy. Venus clouds 9th, the right temperature, catastrophically wrong chemistry. And here's the part I actually find useful. Beyond the list itself, every serious candidate on it is warmed by tidal flexing, not by starlight. That completely changes the arithmetic for the rest of the universe. If liquid water only exists in narrow habitable zones, oceans are rare. If any moon in an elliptical orbit around a giant planet can have one, then oceans might be the most common habitat in the galaxy, and the sunlit surface of a planet like ours might be the unusual case, not the standard one. The other practical thing worth carrying away, Notice how much of this list comes from one flyby, one radar pass, one instrument that happened to be pointed the right way. We ranked Triton off a single afternoon in 1989. We found Enceladus's phosphates by reanalyzing data Cassini collected years before anyone was looking for them. There is almost certainly more sitting in existing data sets right now. Next time, the opposite question. Not where life could be hiding, but why we haven't heard from any of it. The galaxy is 13 billion years old and contains hundreds of billions of stars, and there has been more than enough time for someone to have crossed it many times over. The silence has about a dozen competing explanations, and the most unsettling one isn't aliens being rare. It's what it implies about how long civilizations last. Subscribe, and I'll see you.
There are somewhere between 100 and 400 billion stars in this galaxy, and the galaxy is 13 billion years old. At a tenth of the speed of light, slow by physics, hard by engineering, you could cross the whole 100,000 light-year width of it in about a million years. Against 13 billion, a million years is nothing. There has been time for someone to cross this galaxy end to end thousands of times over. And there is nothing. No signals, no probes, no engineering around other stars. That gap has about a dozen famous explanations, and almost all of them fail the same test for the same reason. I'm going to show you the test, use it, and then give you the one answer that survives, which is not aliens are rare and is not the one you've heard. Here is the test. Suppose there have been a million technological species in this galaxy's history. Now take an explanation like they all decided not to explore. That has to be true a million times, not usually, every time, without one exception across billions of years and a million separately evolved cultures. Because one exception, one species out of a million that does spread, produces exactly the galaxy we don't see. That's the uniformity problem. And once you're holding it, most of the famous answers fall apart in about 10 seconds each. The zoo hypothesis. They know we're here and they've agreed to leave us alone. That's a galactic non-interference treaty with no enforcement, no defectors, forever. Not one hobbyist, not one splinter group. They're already here, the UFO answer. Set aside the evidence problem for a second. Even granting visitors, it explains nothing else. Why the silence? Why no engineering anywhere? The dark forest. Everyone stays quiet because announcing yourself is suicide. This one is genuinely clever, and it still fails, but for a different reason. Hiding requires energy. Energy makes waste heat, and waste heat is thermodynamically impossible to hide. It has to radiate at infrared wavelengths we can survey. Dark forest predicts a silent galaxy full of hidden industry. We see the silence, we don't see the industry. They're all sleeping. A real proposal from Oxford, and the physics is sound, computation gets cheaper as the universe cools, so a civilization that mainly wants to think would wait. But it needs every civilization to be patient, and dormant hardware still has to survive, which means infrastructure we should be able to see. 4 famous answers, 1 shared flaw. If an explanation needs a million independent species to make the identical choice, it isn't an explanation, it's a wish. Now, the ones that survive, because they don't ask anyone to choose anything. First, we have barely looked. In 2018, a group of astronomers tried to quantify how much of the search we've actually done. The search space has many dimensions: which stars, which frequencies, how sensitive, how long you listen, what kind of signal you assume. Their answer is the number worth remembering. The total volume of the search completed so far is comparable to scooping 1 hot tub of water out of Earth's oceans, finding no fish, and concluding the ocean is empty. It is very hard to be confused about an absence of signals when you have examined a rounding error's worth of the places a signal could be. Second, interstellar travel may be much harder than we assume. The problem isn't distance. At a tenth of light speed, every hydrogen atom in your path arrives with the energy of a particle accelerator, continuously for decades. Every dust grain is a nuclear-scale collision.
and everything aboard has to keep working for centuries with no resupply. Robotic probes are easier, which is why self-replicating machines are the strong form of the paradox. But that means a machine that finds raw material in an alien system, refines it, and builds a working copy of itself, indefinitely, with errors accumulating every generation. We have never built anything close to that on Earth, with an atmosphere, a supply chain, and a workforce. Notice this one doesn't need uniform behavior, just uniform physics. That's a far more defensible claim. Third, the Great Filter. In 1996, the economist Robin Hanson pointed out that getting from dead chemistry to a galactic civilization requires passing a long series of steps. Life starting it all, complex cells, intelligence, technology, surviving technology. The silence tells us at least one of those steps is nearly impassable. The question is whether it's behind us or in front of us. And this is the part that should stop you. Finding simple alien life would be bad news. It would mean the early steps are easy, which pushes the filter toward the part we haven't done yet. So here's the answer I'd actually bet on. It's the most recent one, and almost nobody outside the field has heard it. It starts by changing the question. Not how many civilizations are there, but given that we exist, when should we expect to find ourselves? Think about what an expanding civilization does to a galaxy. It fills it. Once one appears on cosmic timescales, it converts everything reachable fast, which means a new civilization can only ever arise in a region nobody has reached yet. And the longer the universe runs, the less such space is left. So there's a deadline built into the structure of the universe. Late arrivals don't get to arise at all because their region is already claimed. Anyone who exists to ask this question must, by construction, have arrived early. Run the timing, and here's where we are. The universe is 13.8 billion years old. Stars will keep forming for trillions of years. We are inside the first 1% of the habitable era of this universe. Asking why the galaxy is empty right now is like showing up at a venue an hour before it opens and wondering where everyone is. This is the only answer that passes every test. It explains the whole silence, not a slice of it. No signals, no probes, no engineering, because there is nobody yet. It requires zero uniformity of behavior because it isn't about behavior at all. And it makes real predictions about how far away the nearest expanding civilization should be. It also flips the emotional weight of the whole question. If we're early, the silence isn't a warning. It's an opening. Everything is unclaimed. Two things to take with you. The first is a filter you can use for the rest of your life. Next time you hear the Fermi paradox discussed, listen for whether the answer requires 1 million independent species to make the same choice. Zoo hypothesis, dark forest, they all went quiet, they all went virtual. Every one of them needs that, and every one of them fails on it. The most repeated answers are the weakest ones, and popularity has kept them alive long past their expiry date. The second is that this stops being philosophy very soon. Every serious explanation here makes a prediction about biosignatures, and we are entering the decade where we can measure them. Telescopes operating right now can examine the atmospheres of rocky planets around small stars, and the next generation is being built specifically for this. If simple life turns out to be everywhere, the Great Filter is in front of us, and this becomes a much darker story. If even simple life is rare, then the filter is behind us. We already got through it, and the emptiness isn't a warning, it's an inheritance. Nobody knows which yet, but for the first time since Fermi asked the question over lunch in 1950, it has stopped being a thought experiment and become a measurement we're about to make. Next time, the machines we've already sent out of the solar system. One of them is still transmitting from over 20 billion kilometers away using less power than the light in your fridge. And what happens to them over the next billion years is far stranger than where they're going. Subscribe, and I'll see you there.
You probably think the Earth ends in fire, or ice, or an asteroid, something dramatic, something with a countdown. Most of the ways this planet actually ends are quieter than that, and several of them are already underway. I've sorted every credible way the Earth could end into 8 tiers.
from the ones that merely knock civilization over to the one that erases the planet from existence entirely. Each tier is more final than the last, and I'm going to tell you which are survivable, which are guaranteed, and roughly when. The last one on this list is certain. It has a date, and nothing anyone will ever build can stop it. Let's start small. Tier 1. The events that end civilization, but not the planet. A solar flare sounds harmless? It is not. In 1859, the sun fired a coronal mass ejection directly at Earth in what's now called the Carrington event. Telegraph lines sparked. Operators got shocks. Some telegraph systems kept transmitting after being disconnected from their batteries, running on current induced by the sky itself. That was in a world with almost no electrical infrastructure. A Carrington-class event today would induce currents in long conductors, power lines, pipelines, undersea cables. The vulnerable part is the large transformers at the heart of the grid. They are custom-built, they weigh hundreds of tons, and there is no warehouse of spares. Replacement is measured in months to years. Estimates of the odds of a Carrington-scale event in any given decade run in the low single-digit %. Over a human lifetime, that is not a small number. Then there's the supervolcano. Around 74,000 years ago, Toba in Sumatra erupted with a force that dwarfs anything in recorded history. It put enough sulfate into the stratosphere to cool the planet for years. There's a long-running hypothesis that this event drove human populations down to a bottleneck of a few thousand individuals. Genuinely debated, not settled, but the eruption itself is not in doubt. Yellowstone gets the headlines. The USGS puts the annual probability of a Yellowstone supereruption at roughly 1 in 730,000, and notes there's no indication of one being imminent. The real risk is that there were dozens of such systems worldwide, and we only monitor some of them closely. And the third in this tier is the one you have already lived through a smaller version of, a pandemic. The 1918 influenza killed somewhere between 50 and 100 million people in a world of under 2 billion, with no air travel. None of these end the Earth. They end the arrangement humans have made on top of it, which, for you, is arguably the same thing.
Tier 2. Impact. 66 million years ago, an object roughly 10 to 15 kilometers across struck what is now the Yucatan Peninsula. The Chicxulub impact released energy in the range of 100 million megatons, orders of magnitude beyond the entire global nuclear arsenal, and ended roughly 3/4 of all species on Earth, including every non-avian dinosaur. The killing mechanism was not the impact. It was the dust and sulfate aerosol thrown into the stratosphere, which shut down photosynthesis. The food chain collapsed from the bottom. Here is the part that surprises people. This is the one item on the entire list we can currently do something about. In September 2022, NASA deliberately crashed a spacecraft into a small asteroid moon called Dimorphos to see whether a kinetic impact could change its orbit. It worked better than predicted. The orbital period shifted by about 32 minutes. The target had been a change of 73 seconds or more. That is a real demonstrated planetary defense capability, on the condition that we spot the object with years of warning. Surveys have found most of the kilometer-plus near-Earth asteroids. The smaller city killers are far less completely cataloged. So Tier 2 has an asterisk. Dangerous, historically proven, and uniquely on this list, partially solved. Tier 3. The ones we're doing to ourselves. There are roughly 12,000 nuclear warheads on Earth. The direct blast effects would be catastrophic and regional. The mechanism that would make it global is nuclear winter. Firestorms and burning cities lofting soot into the stratosphere where there is no rain to wash it out, dropping global temperatures and collapsing agriculture for years. The modeling here is genuinely contested. Soot injection estimates vary widely, and some researchers argue the severe scenarios overstated. But the physical mechanism is the same one that makes supervolcanoes and asteroid impacts lethal: block the sun, break the food supply. Alongside that sits engineered biology. A natural pathogen faces an evolutionary trade-off: kill too fast and you stop spreading. A designed one does not necessarily face that constraint. This is the risk category that has grown fastest. because the cost of the underlying technology has fallen fastest. Notice the pattern across tiers 1 to 3. Almost nothing kills by direct violence. Nearly everything kills by blocking sunlight and breaking agriculture. If you wanted one sentence for how planets become uninhabitable, that's it.
Tier 4. Runaway climate. Earth has a neighbor that already did this. Venus is nearly the same size as Earth and receives about twice the sunlight, and its surface sits at about 465 degrees Celsius, hot enough to melt lead, and hotter than Mercury despite being further from the sun. The mechanism was a runaway greenhouse. Water evaporated. Water vapor is itself a greenhouse gas, which raised the temperature, which evaporated more water. The feedback ran to completion. Ultraviolet light broke the vapor apart high in the atmosphere, and the hydrogen escaped to space, so the water never came back. Now, the honest version. Current mainstream science does not consider a Venus-style runaway achievable on Earth by burning fossil fuels. Earth is further from the sun, and the threshold appears to be well above anything our carbon reserves can reach. Papers proposing a fossil fuel runaway are outliers. But the same physics does get Earth eventually, from a different cause, and that's the next tier. Tier 5. The sun brightens, and the oceans leave. The sun is not a constant. As it fuses hydrogen, its core contracts and heats, and its output slowly rises. It is roughly 30% brighter now than when Earth formed, and it will keep going. In about 1 billion years, the increase is projected to push Earth past the threshold Venus crossed. Oceans evaporate. Water vapor dominates the atmosphere. Hydrogen is lost to space permanently. Before that, something subtler and arguably sadder happens. Higher temperatures accelerate the weathering of silicate rock, which pulls carbon dioxide out of the atmosphere. Below a certain concentration, standard photosynthesis stops working. On timescales of a few 100 million years, most plant life becomes impossible, long before the oceans are gone. There is no scenario where humanity survives this in place. It is not an emergency. It's a deadline with 9 zeros on it. Tier 6. The sun eats the inner solar system. In about 5 billion years, the sun exhausts the hydrogen in its core, and the outer layers swell into a red giant. Its radius grows by a factor of more than 200. Mercury and Venus are certainly consumed. Earth is genuinely uncertain, and the uncertainty is interesting. As the sun expands, it also loses mass through an intensified solar wind, which weakens its gravitational grip and lets Earth's orbit widen. So there's a race between the expanding surface and the retreating orbit. Recent modeling mostly favors Earth being engulfed anyway, dragged in by tidal interaction with the sun's bloated outer envelope. But even in the version where Earth survives physically, it survives as a scorched, airless rock orbiting a dying star. The distinction is academic. After that, the sun sheds its outer layers and leaves a white dwarf, an Earth-sized ember that cools for trillions of years.
Tier 7. The galactic collision, which is the gentlest item on this list. The Andromeda Galaxy is approaching the Milky Way at around 110 kilometers per second, and the two are expected to interact in roughly 4 to 5 billion years. Everyone imagines catastrophe. The reality is almost comic. Galaxies are overwhelmingly empty. The typical separation between stars is millions of times their diameter. In a galactic collision, the odds of any two stars actually hitting are effectively zero. What actually happens is gravitational rearrangement. Orbits are stretched and flung. The two galaxies eventually merge into a single elliptical galaxy. The night sky would be extraordinary. The ground under your feet would not notice. Worth adding, recent Gaia-based analyses have downgraded this from certainty to roughly a coin flip over the next 10 billion years. Even the galactic collision is less dramatic than advertised.
Tier 8. The end that has no survivors and no exceptions. Everything so far is local. This one is the universe itself. Current observations indicate the expansion of the universe is accelerating, driven by dark energy. If dark energy behaves as a cosmological constant,
the universe expands forever and cools toward heat death. Stars burn out, matter disperses, and eventually, no process anywhere can extract useful energy. Nothing can happen. There is no version of surviving that. The timescale is beyond intuition, a Google years for the last black holes to evaporate. There is a more abrupt possibility. If dark energy strengthens over time, expansion could tear apart galaxies, then solar systems, then atoms in a big rip. Some analyses put that at tens of billions of years, though it is not the favored model. And there is the strangest one, vacuum decay. If our universe's vacuum is not in its lowest possible energy state, a bubble of true vacuum could nucleate somewhere and expand at the speed of light, rewriting physics inside it. You would receive no warning because the warning would arrive at the same instant as the bubble. Measurements of the Higgs boson and top quark mass put us intriguingly close to the boundary between stable and metastable. The estimated timescale is vastly longer than the current age of the universe, and one detail I find genuinely funny, this is the only entry on the list where you are guaranteed not to suffer, because there is no interval between fine and gone.
So here's the whole list, sorted. Solar flare, supervolcano, and pandemic end civilization, not the planet. An asteroid impact could do far worse, and is the only one we have already demonstrated a defense against. Nuclear winter and engineered pathogens are self-inflicted, and the only ones with a decision maker. Runaway greenhouse ends Earth's habitability in about 1 billion years. The red giant ends the planet in about 5 billion. The Andromeda collision, despite the branding, barely counts. And heat death ends the possibility of anything happening at all. 2 things stand out to me from putting it in this order. First, almost every near-term extinction mechanism works the same way. Put something in the stratosphere, block sunlight, break agriculture. Soot, dust, sulfate. Different causes, one killing mechanism. That's a genuinely useful thing to know because it means resilience against one buys you resilience against most. Second, and this is the part worth taking with you, exactly one item on this list has a proven countermeasure, and we built it in 2022 by hitting a rock in space and measuring how much it moved. Everything above Tier 2 is out of reach for now. Everything at Tier 3 is a choice, not a physical law. So the honest summary is that the Oath is going to end, on a schedule, and the only entries anyone alive can influence are the ones we would be doing to ourselves. Next time, I'm doing the opposite of this list. Every place in the solar system where life could actually still exist right now, including a moon with more liquid water than every ocean on Earth combined, hidden under an ice shell. And the reason we haven't drilled into it yet is not technical. Subscribe, and I'll see you there.
There is a liquid that stands up when you bring a magnet near it. Not ripples, not a bulge. It grows a forest of perfect black spikes, arranged in a pattern so precise, you could calculate it with an equation. It looks like special effects. It looks like something that should not be allowed to exist in a bottle on a desk. And the strangest part of the story is not what it does. It is where it came from and where it ended up. It was invented at NASA in the 1960s to solve a very specific problem with rocket fuel. It never flew on a single rocket. Instead, it quietly moved into your house. It is almost certainly inside the speakers you are listening to me on right now. It spent decades inside nearly every hard drive on Earth, and there are doctors testing it as a way to steer chemotherapy through your bloodstream to a tumor and nowhere else. This is the story of the strangest liquid humans have ever made, and how a failed rocket experiment ended up in 1 billion living rooms. Let's start with the problem NASA actually had, because it is the kind of problem you never think about until you leave Earth. On the ground, fuel behaves itself. Gravity pulls it to the bottom of the tank, the pump sits at the bottom, and the pump gets fuel. Simple. In orbit, there is no bottom. Fuel in a weightless tank does not sit anywhere. It drifts. It clings to the walls in sheets, it forms floating blobs in the middle of the tank, and when the pump switches on, it might get liquid. Or it might get a mouthful of vapor, which is a very bad thing to feed an engine you are relying on to get home. Engineers had ugly workarounds. Fire small thrusters first to shove the whole spacecraft forward so the fuel sloshes to one end. Put a flexible bladder in the tank and squeeze it. Both work. Both add weight, moving parts, and new ways to fail. So in 1963, an engineer at NASA named Steve Papel asked a different question. What if you did not have to chase the fuel around the tank? What if you could just reach in with a magnet and pull it where you wanted it? The obvious objection is that fuel is not magnetic. Neither is water or oil or almost any liquid you have ever met. His answer was, then let's make it magnetic.
Here is the trick, and it is more elegant than it sounds. You can't just melt a magnet. Heat a piece of iron enough to turn it into liquid, and it stops being magnetic entirely. The temperature scrambles the internal alignment that made it a magnet in the first place. So Papel went the other direction. Instead of making a magnet into a liquid, he put solid magnets into a liquid. He ground magnetite into particles about 10 nanometers across. That is small enough that a single grain contains only a few thousand atoms, and small enough that the random jostling of the liquid's own molecules keeps them permanently suspended. They never settle the way sand settles in water, because at that scale, they are being kicked around faster than gravity can pull them down. But there is a catch, and it is the catch that makes this hard. Magnetic particles want to stick to each other. Left alone, they clump into useless grit within minutes. So every single particle gets wrapped in a molecular coating, a layer of long, slippery molecules that keep the particles from ever quite touching. Get all three parts right, particle size, coating, carrier liquid, and you get something genuinely new. A liquid that responds to a magnet as a whole while staying perfectly liquid. Pour it, splash it, spill it. It is a fluid in every way, right up until a magnet walks into the room. And then you bring the magnet close, and it does the thing. The spikes are not decoration. They are the fluid solving a maths problem in real time. Three forces are arguing. The magnetic field wants the fluid to pile up along the field lines, stretching upward. Gravity wants it flat. Surface tension wants the smallest possible surface area, which also wants it flat. Below a certain field strength, flat wins and nothing happens. Push past that threshold and the magnetic force overwhelms both, and the surface breaks into the most efficient possible compromise, a repeating array of peaks. The shape is called the Rosenzweig instability, and the spacing between spikes is not random. It is set by the properties of the liquid, and you can predict it on paper. Which means when you watch a ferrofluid spike up, you are watching an equation happen. Now, the twist. NASA never used it. The fuel problem got solved other ways. Bladders and settling burns turned out to be good enough, and nobody wanted to fly a tank full of experimental magnetic sludge. The idea sat there, a solution that worked beautifully, attached to a problem that had already moved on. That could easily have been the end, a curiosity in a patent file.
What saved it was a completely different property, and one nobody was excited about at first. Ferrofluid stays exactly where you put it. Take a spinning shaft passing through a wall, the wall of a vacuum chamber or a sealed hard drive. Sealing that gap is a genuinely annoying engineering problem. A rubber seal touches the shaft, so it creates friction, generates heat, and wears out. A gap with no seal lets contamination through. Now, put a ring magnet around the shaft and a drop of ferrofluid in the gap. The fluid locks into place in the field, forming a liquid ring that completely fills the space. And it stays there because the magnet will not let it leave. The shaft spins freely through it. Nothing touches, nothing wears, nothing gets past. For decades, that seal sat inside hard drives, keeping dust away from platters spinning at 7,000 revolutions per minute, where a single speck of dust is a catastrophe. It is in semiconductor manufacturing equipment and in vacuum systems where a leak means starting over. And then there is the one in your room. Look inside almost any loudspeaker and you will find a coil of wire sitting in the gap of a permanent magnet. Music is that coil pushing back and forth, but a coil carrying current also gets hot, and heat is a speaker's enemy. It changes the sound, and eventually it kills the driver. So somebody realized there is already a strong magnet right there. Put a drop of ferrofluid in the gap and it stays put. in permanent contact with both the coil and the metal around it, carrying heat away far faster than air ever could. It also damps unwanted resonance, and it costs almost nothing. Hundreds of millions of speakers have been built this way. A failed rocket experiment is in your headphones, your car doors, your television, doing a quiet job, holding on with nothing but a magnetic field.
Which brings us to where this is going. And this is the part that could actually matter. If you can steer a liquid with a magnet from outside the container, then you can steer a liquid inside a human being. Chemotherapy has a brutal design flaw. You put poison in the bloodstream, and it goes everywhere. The tumor gets some, so does everything else, which is where the side effects come from. The idea being tested is to attach the drug to magnetic nanoparticles, inject them, and hold a strong magnet over the tumor. The particles concentrate in that region, so the dose lands where you want it, and the rest of the body gets less. In animal studies, this works. Human trials are ongoing, and it is genuinely hard. Magnetic fields fall off fast with distance, so reaching a tumor deep inside the body is a real problem, not a detail. A related version is already routine, though. Those same coated iron oxide particles are used as contrast agents in MRI scanners, making certain tissues light up. And there is a treatment called magnetic hyperthermia, where the particles are injected into a tumor and then hit with a rapidly alternating field. The particles cannot flip fast enough to keep up, and the lag turns into heat, cooking the tumor from the inside at a temperature the surrounding tissue survives. There is also a strange, delightful branch, soft robotics, blobs of magnetic fluid that can be steered through a tube, change shape, split apart, and merge back together, all from outside. Researchers have driven them through models of the digestive tract to deliver a payload to one specific spot. Every one of those applications traces back to a tank of rocket fuel that nobody could pour. So here is what I actually take away from this. Steve Bappel solved his problem. He built the thing, it worked, he patented it, and then the mission requirement it was designed for evaporated. By the only measure anyone was using at the time, that project failed. 60 years later, his failed invention is in your speakers, it was in your hard drives, and it might one day be threading chemotherapy through someone's bloodstream to exactly the right place. The invention was fine. The problem it was aimed at was just the wrong one, and it took decades for the right problems to show up. If you like the idea that the useful thing and the intended thing are often not the same thing, stick around. Next time, we're going to look at a lamp that floats in mid-air above its base, with nothing holding it up, and a mathematical theorem from 1839 that proves rigorously that what you are looking at is impossible. The lamp is not breaking the theorem. It is cheating, and the way it cheats is the same technology as a 600-kilometer-an-hour train. Subscribe, and I'll see you there.
There is a toy that has been sitting on desks for 80 years, dipping its beak into a glass of water, standing up, and doing it again. No batteries, no motor, no winding, just a glass bird, bobbing, apparently forever. In 1922 in Shanghai, someone showed one of these to Albert Einstein. He was, at that point, arguably the most famous physicist alive, 1 year off a Nobel Prize. And he did what any physicist would do. He looked at it, worked out what he thought was happening, and explained it. The account we have says he got it wrong. That is the interesting part. Not that a toy is clever, but that a toy is clever in a way that fools the person you would least expect it to fool. Because the drinking bird is not doing the obvious thing. It is not a novelty. It is a heat engine, the same category of machine as a steam locomotive. And it is running on something you cannot feel, and would never think to call a fuel. Let's find out what is actually powering it, and why, if you put it in a sealed box, it dies.
Before we get to how it works, we should talk about what it is not. Because for 300 years, people have wanted this to be something it isn't. The dream is perpetual motion, a machine that runs forever, producing more energy than you put in. It is impossible. The laws of thermodynamics are not suggestions, and the first one says you cannot create energy from nothing. But That has never stopped anyone from claiming they had. The most spectacular case is Charles Redheffer in Philadelphia, 1812. He built a machine that appeared to turn on its own, exhibited it, took money from crowds, and petitioned the state for funding to build a bigger one. Inspectors came. And in a detail I find genuinely delightful, one of them noticed the gear teeth were worn on the wrong side. The pattern showed the machine was being driven from the output shaft, not driving it. He moved to New York and tried again. This time, a group including the engineer Robert Fulton went to see it. Fulton listened, then pointed out the machine was running at a slightly irregular speed, which no purely mechanical drive would do. He asked to remove some boards from the wall. Behind them was a belt, running up through the building to an attic, where an old man sat turning a crank by hand while eating bread. So when a small glass bird appears to move forever with no power source, the instinct to yell fraud is well earned. Except this time, the bird is not lying, just is not telling you where the energy comes from.
Here is what is inside it. The bird is 2 glass bulbs joined by a tube. The tube runs from the bottom of the lower bulb almost all the way up into the head. Inside is a liquid, usually methylene chloride dyed red, and critically, the air was pumped out before sealing. So above the liquid, there is no air. There is only vapor of the liquid itself. That detail is the whole trick, and here's why. Methylene chloride boils at about 39 degrees Celsius. Far lower than water, and in a sealed space with no air, the pressure inside is entirely determined by the temperature of the liquid. Warm it slightly, more evaporates, pressure rises. Cool it slightly, vapor condenses, pressure drops. The pressure is a direct readout of temperature, and it is very sensitive. Now, the head is covered in felt, and you wet it. Water evaporating from that felt takes heat with it. This is the same reason you feel cold stepping out of a shower. So the head becomes slightly cooler than the body. We're talking a few degrees, not dramatic, but a few degrees is enough. Vapor in the cooler head condenses, pressure in the head falls, and the higher pressure down in the warm belly pushes liquid up the tube into the head. Now the bird is top heavy. It tips forward. Its beak goes into the water, which re-wets the felt, which is what keeps this running. And when it tips far enough, the bottom of the tube lifts out of the liquid in the belly. Vapor rushes up, pressure equalizes, and the liquid in the head drains back down. The bird becomes bottom heavy again and stands up. Then it starts over. So what is the fuel? Not the water. The bird will run over a glass of water for weeks, and the water level barely moves. The fuel is the difference between how much moisture the air is holding and how much it could hold. Dry air pulls water out of the felt fast, cooling the head hard, and the bird nods quickly. Humid air pulls slowly, and the bird gets sluggish. It is drinking the dryness of the room, which gives us the most satisfying test in the whole story. Put the bird inside a sealed jar with its glass of water. Nothing else changes. Same temperature, same water, same bird. Over the next few hours, the air in the jar saturates with moisture. Evaporation stops, the head can no longer get cooler than the body, and the bird slows down and comes to a stop. Not because it broke, because it ran out of fuel. Exactly like a car. Open the jar, and it starts again. That is what makes it a real heat engine, and not a trick. It takes heat from one place, dumps it somewhere colder, and turns the difference into motion. That is the same sentence you would write about a power station. The bird just does it with a temperature difference so small you cannot feel it with your hand. And this is where Einstein comes in. The account says he assumed the mechanism was the evaporating water doing work directly. A reasonable first guess, and wrong. The bird is a closed system. The water outside never enters. It only steals heat from the head. The real engine is the vapor pressure difference inside sealed glass, driven by that tiny temperature gap, which is a lovely reminder that obvious and correct are not the same thing, even at that altitude. The bird also has a much less charming history than you would expect, and a much more serious future. The patent most people point to was filed in 1945 by Miles Sullivan, a scientist at Bell Labs, the research lab that also produced the transistor, the laser, and information theory, a place that changed the 20th century, also mass-produced a bobbing glass duck. But the design is older than that. Similar devices circulated in China well before, which is why the Shanghai story exists at all. For decades, it was purely a toy. Then people started noticing something. The bird is a machine that converts a temperature difference of a few degrees into mechanical motion, using no rare materials, no electronics, and no maintenance. And the world is absolutely full of small temperature differences going to waste. There have been demonstrations of drinking birds hooked to tiny generators, producing small amounts of electricity. In 2024, a research group published work on a drinking bird-based generator that harvested energy from evaporation and produced enough to run small electronic devices. Genuinely published, not a viral claim. The power is tiny. Nobody is running a house on this. But there is a real category of application where tiny is enough. A sensor in a field, in a wall, in a pipe that needs microwatts and must never have its battery changed. Evaporation happens continuously, everywhere, for free. There is something very funny about the possibility that a toy invented to amuse people ends up powering infrastructure sensors, having spent 80 years being underestimated on desks.
Let me put the whole thing back together. A glass bird sits on your desk, apparently moving forever. It is not. It is a sealed heat engine running on a temperature difference of a couple of degrees, created by water evaporating from a wet felt head, made possible because someone pumped the air out and used a liquid that boils near room temperature. Its fuel is the dryness of the air in your room, which is why it dies in a sealed jar and revives when you open it. It fooled Einstein, at least according to the story, because the real mechanism is invisible and sealed inside glass, while the visible thing, a bird drinking water, is a decoy. And that is the part I keep thinking about. The most interesting machines are often the ones where the obvious explanation is the wrong one, and the actual explanation is quieter and stranger. Next time, something that looks even more impossible. A lamp with a floating moon hovering in mid-air above its base, with nothing touching it and nothing holding it up. There is a mathematical theorem from 1839 that proves rigorously that stable magnetic levitation cannot happen. Nobody has ever disproved it. The lamp is not disproving it. It is cheating. And the cheat is the same technology that moves a 600-kilometer-an-hour train. Subscribe, and I'll see you there.
In 1839, a British mathematician named Samuel Earnshaw proved something inconvenient. He showed rigorously that you cannot hold an object stable in mid-air using magnets alone. Not we haven't figured it out yet, not it's very difficult, mathematically impossible given fixed magnets and gravity. Nobody has ever overturned it. It is still true today. It is taught in physics courses as a theorem, not a debate. And yet, you can buy, for about $30, a lamp with a small model of the moon hovering in mid-air above a wooden base. Nothing touches it. You can pass your hand through the gap. It glows and it slowly spins, and it stays there for years. So one of two things is happening. Either a 19th century theorem is wrong, or that lamp is cheating. It is cheating. And the specific way it cheats is the same principle that moves a train at 600 kilometers an hour, and the same principle behind a physicist who once levitated a live frog and won a prize for it. Let's take it apart.
First, why is levitation supposed to be impossible? Because the intuition, just push up as hard as gravity pulls down, turns out not to be enough. Imagine balancing a marble on top of a perfectly smooth dome. There is exactly one point where the forces balance. In theory, it could sit there forever. In practice, it never does. The tiniest nudge and it rolls off. And once it starts moving, every force pushes it further away. That is what unstable means. The system does not fight to return. Earnshaw's proof says that any arrangement of fixed magnets creates exactly that situation. There will be a point where forces cancel, but it is always a saddle, never a bowl. Squeeze the object stable in one direction, and it becomes free to escape in another. There is no configuration of static magnets where every direction pushes back toward the center, which is why generations of inventors kept building beautiful magnetic arrangements that almost worked. Set it up perfectly, let go, and it drifts sideways and slams into a magnet. Every time. The theorem was not being unfair to them. It was telling them the answer in advance, and they did not want to hear it.
There are exactly 3 known ways around Earnshaw, and each one works by violating one of the assumptions in his proof. Number 1, diamagnetism. Most materials you can name are either attracted to magnets or ignore them, but a small group are weakly repelled by magnetic fields. Bismuth, graphite, and surprisingly, water. And because you are mostly water, so are you. Earnshaw's proof assumed ordinary magnetic materials. Diamagnetic materials fall outside it, and they can levitate stably with no electronics at all. You just need a very strong field. In 1997, physicist Andre Geim did exactly this in a lab in the Netherlands with a live frog. He put it in a powerful magnetic field, and the frog floated calmly in mid-air. It was unharmed. The experiment won him an Ig Nobel Prize, the award for research that makes you laugh and then think. 10 years later, he won an actual Nobel Prize for isolating graphene. He is the only person to have both, which I find delightful. Number 2, superconductors, which lock a magnetic field in place and pin an object rigidly in the air. Extremely stable, but you need extreme cold, so it stays in the laboratories. And number 3, which is the one in the lamp, don't use fixed magnets at all. Cheat with electronics. Here is what is actually inside that base. There is a sensor, usually a Hall effect sensor, that measures the magnetic field and therefore tells the system how far away the moon currently is. There is an electromagnet, and there is a control circuit joining them. The loop runs roughly like this. The moon drifts down a fraction of a millimeter. The sensor detects the field getting stronger. The circuit increases current to the electromagnet, pulling harder. The moon rises. Now the field weakens, current drops, the moon falls slightly. Repeat. That cycle runs on the order of 1,000 times per second. So the moon is not resting on anything. It is falling constantly and being caught constantly, faster than your eye can resolve. What looks like perfect stillness is actually a very fast argument between gravity and a microcontroller. Earnshaw's theorem is untouched because his proof assumed static fields. The moment the field changes in response to position, you are outside the theorem. The lamp is not breaking a law of physics. It is stepping around the edge of one, using a component that did not exist in 1839. This is called active magnetic levitation, and it is why the lamp must be plugged in. Cut the power, and the moon does not hover for even a moment. It drops immediately because the only thing holding it up was a decision being made 1,000 times a second. There is also a small detail people miss. The moon usually spins, not because anything drives it, but because there is essentially no friction, only air. So any tiny initial push takes a very long time to die away. The same trick, made bigger, becomes transport infrastructure. A maglev train is the lamp's principle scaled up. Instead of a small moon, several hundred tons of train. Instead of one electromagnet, thousands along the track, each adjusting continuously to keep the train floating a few centimeters above the guideway. Remove the wheels, and you remove rolling friction and mechanical wear. What is left is air resistance. A maglev in Japan set a record above 600 kilometers per hour with passengers aboard, and the Shanghai airport line has been carrying commuters at 430 for years. The same idea shows up in less glamorous places too. Flywheel energy storage systems spin heavy rotors on magnetic bearings so nothing touches and nothing wears. Some heart pumps levitate their impeller magnetically so there is no bearing to crush blood cells against. Turbomolecular pumps and some precision machine tools use it for the same reason. And there is one more twist on the lamp itself. Many of these lamps power the light in the floating part wirelessly. A coil in the base creates a changing magnetic field. A coil in the moon picks it up, and current flows across an air gap with nothing connecting them. The same principle as wireless phone charging, discovered by Faraday in the 1830s. So the object is being held up by one magnetic field and lit by another simultaneously. By the way, The surface detail on the better ones is not invented. It is printed from real lunar topography data collected by NASA's Lunar Reconnaissance Orbiter, which has been mapping the moon's surface since 2009.
So let me put it together. A theorem from 1839 says stable magnetic levitation is impossible, and it is still correct. The lamp on your desk does not disprove it. It sidesteps it by making the magnetic field change 1,000 times a second in response to where the object actually is, which is a loophole that only became available once we had cheap sensors and fast electronics. The floating moon is not floating. It is falling and being caught over and over forever. And the catching is so fast that it reads as stillness, which is a decent description of a lot of things that look effortless. Next time, a liquid that stands up into a forest of perfect spikes when you bring a magnet near it. NASA invented it in the 1960s to move rocket fuel in zero gravity. It never flew on a single mission, and then it quietly ended up inside almost every hard drive and hundreds of millions of speakers, including very probably the ones you are listening to right now. Subscribe, and I'll see you there.